Hi, I'm Kmin,
This is Hasan.
and this is our presentation on the Kmin problem. What is the Kmin problem? Given a set of n numbers, find the k smallest value in n. We did this using three different approaches. One being our heap sort, two, our own binary search tree, and three, using C's built-in quicksort. Our first algorithm is the heap sort using heapify or bubble down. An example of a simple heap sort is provided for a visual showing the action of some functions that I will be discussing. First, we construct a heap using heapify with all of our elements from the array. Next, we extract the min value by moving to the end of the array and reheapify it. We repeat this algorithm's action of extracting the min k times and reheapify it each time we do so. This final kth extraction will provide us with the desired k-min value at the array index of n minus k. Since building a heap takes linear time, and extracting the min while reheapifying the heap k times takes log n each time, our worst case time complexity is big O of n plus k times log of n.
Our next algorithm is binary search tree. In order to use binary search tree to find Kmin, we have to load all of our values into a binary search tree. Then we have to find the minimum value of the tree and call successor on the minimum value. Next, we continue to call successor on the return value of each call k minus 1 times. The kth smallest number is found on the final successor call. Our binary search tree stores duplicate values by holding a count of variables at each node, and this allows us to skip any unnecessary predecessor calls. This is done by checking the count of duplicates which are returned from the predecessor call. If the position plus the number of duplicates includes our k value, then we can return the number from the predecessor call. If our k value is larger, then we continue to call predecessor until we find it. In the worst case, building our binary search tree takes big O log n time. It takes big O of n time in the worst case to find the minimum, and calling successor a max of k times takes big O k log n. Our total time is big O n log n plus k log n. We can simplify this down to be big O of n log n.
Our final algorithm is C's built-in quicksort. Once again, a simple quicksort is shown as a visual. In order to find the k-min, you begin by using C's built-in quicksort to order all of the numbers in any given array. After the numbers have been ordered, we know that the k smallest number will be at index k minus 1 in the newly sorted array. The worst case time complexity of quicksort is big O of n squared, and this is because the performance is directly proportional to the square size of the input data, or set n. In order to test the efficiency of our algorithms, a file of 1 million randomly generated numbers is sent through each algorithm, testing for the specified k values. Each algorithm was run multiple times, and an average of elapsed time was taken. Two separate files of 1 million random numbers are used to prove consistency in each algorithm.
These graphs show the average of the two runs are consistent with each other. Heap was the fastest of the three algorithms up to the 250,000th K, and then became the slowest after the 500,000th K. The quicksort algorithm spends most of its time sorting the data, and the data does not change for any iteration of K. This is why quicksort has a fairly consistent time across various Ks. Binary search tree is similar to quicksort in that binary search tree spends most of its time inserting the values into the tree. Making all the successor calls could potentially cause us to see an increase in time as our desired k value grows. We get around this by throwing out duplicates if our k is not within that range. Having duplicate numbers in our data reduces the number of successor calls we needed to make by a factor of 1 over the average number of duplicates. Because the time spent making successor calls was reduced, most of our time is spent on building the tree. This is why we see a similarly consistent time across all k values for the binary search tree. If we allowed less duplicates in our data, we would expect to see this time, a binary search tree, to rise as k rises. The time heap spends on sorting, on the other hand, is greatly affected by the varying k values because it has no way of skipping duplicates within data. It must instead perform k extractions, and that is why we see an increase in the time spent as our k value grows. We conclude our analysis by saying that in cases where we'd be searching for k of 250,000 or less, the heap algorithm was the best choice. When searching for k values of 500,000 or greater, quicksort was the fastest. This is because the time it took to sort all of the numbers and extract the Kmin in constant time outperformed the time it took to build the two other structures and perform the various methods of extraction. In data where duplicates are expected, the binary search tree performs fairly consistent for varying k values, whereas in cases where duplicates are not present, we would expect the binary search tree algorithm to perform slower as k grows, which is similar to the heap algorithm.